In this video, we're going to take a look at a specific type of transformation of a double integral, which we're going to apply our Jacobian process, but the equations, the variables that we're going to be using, or new variables, are not going to be some random pair UV. It's going to be a specific pair of variables, and those variables will form what's called a polar coordinate system, right? So basically, in certain types of double integrals, if we convert to this new coordinate system, right, it will actually make our integrals and our lives a lot easier. So let's just do a quick reminder of the whole polar thing. So let's start by sketching our standard xy plane, our most commonly used pair of variables. So we got our xy. And then let's just pick a point here. It doesn't really matter what quadrant I'm in, but there's point P. And then we have a way of representing this as a ordered pair. So this would be our x, this would be our y, and then so that's one way to identify our point. But that's not the only way to identify points in the plane. We can use different ways of doing it. So one way is, instead of going like horizontally and vertically, why don't we just go directly, or let's say radially, to that point P, right? And we can figure out what that distance is. We know that. And then once we do that and we create this ray, there's automatically going to be an angle right here as well. So we're going to call that angle theta. And this line segment will have a length r. And instead of using x and y, we can represent, that's what that little tilde means, we can represent the same point but with a different pair of variables, all right? Okay, so let me just put a couple of things here. So we have both pairs of variables on my little triangle. So because the Jacobian requires a relationship between our old variables and our new variables, we need to figure out some relationships between xy and r theta. Let me start with probably the most useful pair, and then we'll talk about a couple more. So if we use sine and cosine, and if we take the cosine of that angle theta, so let's write this down. So the cosine of theta, that we know is the length of our adjacent side, which is x, divided by the length of our hypotenuse, which is r, right? And you might even remember this without me even using the word, polar. You might remember this as one of the definitions of the cosine ratio. And then I can solve this for x, and x is equal to r cosine theta. All right? That's good. And if we do something similarly with the sine ratio, the sine of theta, so let's put this over here. Sine is the length of the opposite side, which in this case is y, divided by the same hypotenuse, which is r, so y over r. Do my little bit of algebra. Y is r sine theta. All right. Yeah, so this pair, so basically what we've written down is, just imagine if you know r and theta, so if you know this this new pair that we're using, we could use these equations really simply to figure out the original x and y ordered pair, right? So that's good. So this is an important pair of equations, and it's actually this pair that we're going to use in our Jacobian, right, in a little bit. But before we do that, what if I wanted, instead of having x and y in terms of r and theta, could I find r and theta in terms of x and y? And the answer is yes. So let's say I used Pythagoras, because we have a right triangle there. If I use Pythagoras, Pythagoras tells me that x squared plus y squared is equal to r squared. That's a really nice equation. And if we wanted to solve explicitly for r, if we make the assumption that our radius is going to be greater than or equal to 0, right? Then we can take the square root of both sides, and we can get that r is the square root of this quantity. There you go. So if I know the x and y coordinates, and I assume that r is positive, then I square, add, take the square root, which feels like finding a distance, right? That's exactly what the r represents. It's the distance of the ordered pair from the origin. So that, again, this is a nice equation, really useful equation. Now let's see how we could get something that involves theta. Like we want to be able to express theta in terms of x and y. Well, let's see. We've used 2 of the 3 standard trig ratios. The third one is tangent. And if you notice, if I use tangent, I can get a ratio in terms of y and x, and I don't have to know r, right? In other words, I can use my old pair of variables, and I can say this, that the tangent of theta is the length of the opposite divided by the length of the adjacent. So it's like this. And then, of course, we could take the arctangent. But the thing about the arctangent, you have to remember how some of those inverse trig functions are defined, where there's this restricted domain in order to make them one-to-one, etc., etc. And that's a whole rabbit hole that I'm not going to go down right now. So I'm just actually going to stop at this point. And yes, we could write inverse tangent, but unless I know more about y and x, if I know a little bit more about which quadrant we're in, then I could write a more explicit formula. Otherwise, I'd have to write this crazy piecewise function, which again takes us away from what we want to accomplish. So I'm just going to box that off and say, here you go. Right? So these are the 4, I would say, basic equations that give relationships between these pairs of variables. All right. So, but it's the first pair, the x equation and the y equation. That's what we're going to need because we need to compute a Jacobian. So let's go ahead and do the Jacobian just to see what comes out. And in this case, because we're going from xy to r theta, right? And you'll see why we're going to this is even useful. Our Jacobian will be a function of r and theta, right? We're going to get rid of x and y. And so again, let's set up our determinant. And let's remind ourselves, so it's dx dr, dx d theta, just keeping the order correct, dy dr, and then dy d theta. So let's start with our x equation. In fact, let me use my vertical lines here for the determinant, save some space. Dx dr, that means we're treating theta as a constant, and what we have is a constant times r. When I differentiate that with respect to r, I'm going to be left with my constant. So I'm going to have cosine of theta there. If I differentiate x with respect to theta, then I'm treating r as a constant. The r will come down. It's a constant multiple. The derivative of cosine theta is negative sine theta. So we have negative r sine of theta, right? And then let's repeat with the y equation. So now when I differentiate y with respect to r, again, sine of theta is treated as a constant. It's a constant times r, so that derivative is just the constant. Here we go. And then last one, dy d theta, so partial of y with respect to theta, treating r as a constant. It's a constant multiple. Derivative of sine is cosine, so we have r cosine theta, and there you go. All right, so then let's do our 2x2 determinant. So theta times r cosine theta is r cosine squared theta. And then we have minus negative r sine squared theta. So that becomes a plus r sine squared theta. And then we can take out our r, and we have what will be a very useful idea. Well, not will be, it has been in lots of our courses. This identity, really helpful. And look at that, because cosine squared plus sine squared theta is always equal to 1, our Jacobian just works out to be r, right? And because we are assuming that our radius is greater than or equal to 0, we're not dealing with any negative radii, then our Jacobian is always going to be positive. So I'm not even going to need the absolute value in our formula. So let's actually write down, and this will be a theorem. Again, I'll just state the relevant formulas and then just kind of highlight what's going on. But here's the theorem now that basically summarizes this conversion from xy to r theta using our Jacobian process. So if we have, let's say again, we have some region in the xy plane, and in fact, let me specify xy, and then we're integrating some function that's a function of x and y, it's like that. And then this, our differential in general is dA, so this will be xy. Well, so here is when we do our conversion, we will get a new region. But that region now, and this is big R, not little r like we're using for our radius. So this new region will be in terms of r and theta, right? And then our function, what we're going to do is wherever there's an x, we're going to plug in r cosine theta. Right? Wherever there's a y, we're going to plug in r sine theta. And then now we have to multiply by the absolute value of the Jacobian. But because the Jacobian is the r, it's not a constant, but we're treating r as non-negative, right, greater than or equal to 0. So we'll just have an r there, and then technically we're supposed to have dA, and then this is now in r theta, right? And the dA here could be either dr d theta or d theta dr, depending how we set up our limits, right? And this is the theorem that tells us how to convert from xy to r theta when doing a double integral, right? So this kind of describes the how. Let's now illustrate an example, or use an example to illustrate the why, right? Because that's always a thing. Yeah, there's a lot of stuff we could do in math, but the question is why. So here's our example. Now I'll say this. One of the telltale signs in terms of, yes, we should, if the question doesn't tell us, for instance, to do a polar conversion, if you look at your region and it is some circular region, right, in general, and there are other regions, more general, what we call them polar regions, that we can identify, then something circular, usually it's harder to express in terms of x and y as opposed to in the polar equation, right, or in polar coordinate system. So let's take a look at an example. I'm just going to write down a double integral, and it is the double integral, and then the function is e to the negative, and then the quantity we have x squared plus y squared, like that. And then this is dA. And what is our region? So R is the unit circle, right? The entire unit circle. That's what we're integrating over, all right? So there are a couple key things here. So one, there's the word circle. And circles are so much easier to describe. Like the equation of a circle in a polar coordinate system, so much easier. And then not only that, but in one of the equations that we wrote down earlier, we had a relationship between x squared, y squared, and r squared. So this is also a big indicator that if we were to make this conversion, then it's going to simplify our problem quite a bit. All right, so let's do this. Let's actually sketch what's going on. We always like to see our region, but I'm pretty sure we can all visualize our unit circle. But let's make that vision a reality. So let's do this. All right, so there's our unit circle, radius 1 there, radius 1 there. And remember, this would be the equation in rectangular coordinates. It would be x squared plus y squared because the center is at the origin, and then it would be equal to 1 squared, which is just 1, right? That's our famous thing. But right away, we can start to convert stuff because we know that in the polar coordinate system, we get to replace x squared plus y squared. So this sum of squares just becomes a single square. In fact, what we have is r squared is equal to 1. That's a much simpler equation. And we can take it even further. Because we are we're using the fact that r is greater than or equal to 0. When we take our square root, we don't even need the plus or minus. So our r here is 1. So that's the boundary, right? But since we're integrating over the entire region, which is not just the boundary, but everything inside, in fact, let me actually shade it. Right? So it's actually everything bounded by the unit circle. That's our region right there. Then our radius goes from 0 to 1. So that will be sort of our limits for r, right? So our r between 0 and 1. All right. So that's our r variable. Now we have to think about our theta. Well, this again, it's a standard trig. So if you think about how do we trace out the entire unit circle, right? And now when I say trace out, we don't want to keep tracing out the same thing over and over. So what we're doing is we're looking for the smallest range of theta, right, that will trace out the entire boundary exactly once. Well, to get one full revolution, our theta has to go from 0 to 2 pi. Or I should say that's the standard way to get one full revolution. So there are other intervals for theta we could use, but one standard revolution starts at 0, and then again, just to remind you, if we go counterclockwise, so that's pi over 2, this is pi, this is 3 pi over 2, and then we get back to 2 pi, right? So yeah, if we do from 0 to 2 pi, then we're good to go. And that's our range for theta. Now, I'm not even going to try to keep things in terms of x and y so we can compare the difficulty. No, I'm just going to say, look at this pair of limits that we have now. All the limits are constants, and we love double or triple integrals where the limits are all constants, all right? So that's our region, and we've now expressed it in terms of polar variables. Now let's look at our function, right? So we got our limits, now let's look at our function. Well, that's pretty straightforward, again, because we're going to replace the x squared plus y squared with r squared. So this function over here, this one in our theorem, is basically saying express our function in terms of r and theta. So the function in terms of r and theta, in this case, would be e to the negative, and then just replace what I have highlighted there with r squared. There you go. So again, we've reduced I guess you could say the curve to one variable. We've reduced, the function to one variable, and then let's finish out the rest of this. So we have r, which is always going to be a part of the formula for a polar double integral, and then let's write it down. So I'm just going to write down the new converted integral. Now, since we're going to actually evaluate this, I need to actually set up the iterated integral. So put the actual limits that we have here, and I have to pick an order. Usually, I like to use dr d theta, right? And then I get to say this. I'm going to put the r in, so we have r dr d theta. Sound like a pirate there. And then here's our function. It's e to the negative r squared. And then since I'm choosing to integrate with respect to r first, then the inner integral will have 0 to 1, and then the outer integral will be 0 to 2 pi. That's for my theta. And that's the setup, right? And you notice what we have also, as I said, we actually don't have a function of theta here at all. So let's go ahead and evaluate. So I'm going to evaluate the first integral. Let's do this separately. And we got e to the negative r squared times r dr. This one requires a u sub, because if you look at the quote-unquote inner function here is negative r squared, and we have something very close to its derivative right here. We're missing a constant multiple, but that's fixable. So let's let our u be, now this u is just a basic u sub. This is not a u as in the Jacobian type of u, although in some sense they're related. So this is negative r squared, and then our du is negative 2r dr. So there's that constant that I'm missing. So I'm going to multiply both sides by negative 1/2. So negative 1/2 du is r dr. So we take care of that differential. And then love to switch my limits. So when r is 0, my u is also 0. That's nice, right? When my r is 1, my u is negative 1. So it looks a little strange, but let's write down when we do our u sub. So the lower limit is still 0. The upper limit is now negative 1. It seems like it's kind of flipped, but we can actually fix that. And then the function is now e to the u, and then we have that negative 1/2 du. Now, if you don't want to apply the property that I'm about to apply, you don't have to. You could just do the problem and treat it like, even though the limits seem to be a little bit switched, that's fine. But if you wanted to write this so that it bothers you less, remember, when you multiply a definite integral by a negative, you can remove the negative by reversing the limits, by switching the limits. So the property is basically this. If you have this, and let's say you put a negative in front of this, it's the same as now going from B to A. You're basically just kind of flipping the formula of the FTC. So you can use this property to, if you want to remove additional negative sign. So if I remove the negative sign here and just take out a 1/2, then I get to put the lower limit as negative 1 and the upper limit as 0, and then we have our e to the u du. So now let's use our FTC. Antiderivative is 1/2 e to the u. There are limits, and then when we evaluate, we have 1/2, and then we have e to the 0, which is 1, and then minus e to the negative 1. So after doing the inner integral, the first integral, we end up having 1/2 of 1 minus e to the negative 1. All right? But here's the nice thing. This is now just a constant, right? There is no theta left in this. Well, there's no theta to begin with in our original integral. So we just get to integrate that constant from 0 to 2 pi. So the second integral, to finish this example, is the integral from 0 to 2 pi. And we have 1/2 times 1 minus e to the negative 1 d theta. Now again, you might remember some properties about integrals where you're integrating just a constant, but if you don't want to overthink it and maybe use a property incorrectly, you can still apply your fundamental theorem. The antiderivative of this constant with respect to theta is just that constant times theta. So it's 1/2 times the quantity 1 minus e to the negative 1 times theta, and then evaluate it at 0 and at 2 pi. So at the upper limit, you'll have 1/2 times the quantity 1 minus e to the negative 1 times 2 pi, and then at the lower limit, we'll have 0. So the 2 and the 1/2, those reduce to 1. So here's our final answer. It's the quantity 1 minus e to the negative 1 times pi. And that's the value of that double integral. And if we had tried to set this up just using x and y, whether we tried to do type 1 or type 2, it would be a mess. Not only that, but this function, trying to integrate either with respect to x first or y first, good luck with that. All right, so needless to say, this is a pretty good example that illustrates the process, and it's not just kind of a, hey, this is a nice thing to do. This is a super efficient thing to do. So hopefully that helped, and then we're going to continue looking at other types of specific transformations, also in triple integrals. If you can't wait for that, well, we'll see you in the next video.